let's start. Today we have Andrei Parnachev, and he will talk about stress tensor and conformal correlators. Welcome to start.
Okay, great. Thank you. Can you hear me now? Because I'm not sure if my microphone is working.
Yes, but the screen is not particularly well visible, but yeah, this is better. This is better.
Okay, great. So shall I start?
Yeah, you can start.
Okay. Thank you very much for having me. It's a real pleasure to be here. Today I will talk about stress tensor and conformal correlators. And this is based on work that we did in collaboration with Robin Carlson, Manuel Alexisi, Kim Sang-ge, Kavol Sen, and Peter Tadic in Dublin. So let me start by reminding you a few facts about conformal field theories. So in conformal field theories, in these space-time dimensions, an important set of observables are primary operators, which are annihilated by special conformal transformation. And they have definite scaling under the space-time rotations, where you just take every coordinate and multiply it by a constant, which is generated by the rotation operator. And the eigenvalue of the rotation operator is called the conformal dimension of the operator. So all other operators are descendants of the primaries, and they're basically derivatives acting on the primaries. Because of so much symmetries in conformal field theories, 2 and 3 point functions or correlators of 2 and 3 operators are completely fixed by word identities. And in particular, 2 point function of 2 operators is only non-zero when you have the same conformal dimension and behave like 1 over x with 2 delta. And the 3 point function is also fixed. The coefficient that appears in the 3 point function is an important quantity. It's called the OPE coefficient, or coefficient in the operator product expansion. And it appears in the operator product expansion when I take 2 operators, one at position x, another at position 0, then I can expand them in the basis of local operators at position 0, and the powers of x are completely fixed by scaling, and the coefficients which appear here are precisely these OPE coefficients. You can see it by using these 2 identities. If you add another operator here, take an expectation value, use this, and you'll see that these are precisely coefficients in a different function. Now, things become more interesting when we start talking about 4 point functions. So here, let's consider an example where we have a 4 point function of 4 operators which are pairwise identical, and 2 of them are inserted from 0 to infinity, and 2 of them are inserted at 1 in the bar. I can always use conformal invariance to place a position. So these 3 operators, infinity, 1, and 0. So everything depends on 2 variables called cross ratios. They basically correspond to the position of the insertion of this operator. And the 4 point function of this type in CFTs admits a conformal block decomposition, where each conformal block is a known function, and it contains the contribution of the corresponding primary operator and all of its descendants. And the coefficients here, so all the dynamic information about the CFT sits in these coefficients here, and these are the OPE coefficients. So this involves the OPE coefficients of these two operators with operator K, and the OPE coefficients of these two guys with operator K. And in this particular operator K, this particular case, K is characterized by its spin and the conformal dimension. And the way it's written in the channel where we take O1's operators, but where we take Z bar close to 1. So we take O2 operators close together and the 1 operator close together.
What we have on the left is just primary.
Yeah. Now, another important object in CFT, in any CFT, is a stress tensor. And the stress tensor two-point function is completely fixed again. So it has this 1 over x to 2d power times some index structure, where this index structure is this object. And it's fixed up to an overall coefficient. So this overall coefficient is called the central charge. And in what I'm going to talk about today, I will discuss the situation where the central charge is much, much larger than 1. So I'll also refer to these CFTs as large M CFTs for obvious reasons. So let's say in n equals 4 Cyprian mills, which is one of the examples of a CFT, the central charge is proportional to n squared, where n is the gauge, is the rank of the gauge group. Yeah.
Maybe question. So for other operators, you usually just redefine them free scale so that they factor with 1. And for stress energy density.
Yeah, it's canonical normalized stress tensor. So in the following, we'll see what happens when there is scale. So in large CFTs, major players are so-called double trace operators, which are schematically two primary operators with a bunch of derivatives and bunch of derivatives contracted in circuit. So these operators have spin L and conformal dimension 2 delta plus L plus 2n. And for unit normalized operators, the OPE coefficients of operator 1 with a double trace operator order 1, and the OPE coefficients with O1s with the double trace operators of different types are suppressed by a factor of CT. Now, of course, an important example of conformal field theories are conformal field theories which admit holographic interpretation that are dual to gravity in anti-de Sitter spacetime. And d-dimensional CFTs are related to theories of gravity in d+1 dimensional ADS. And here is the usual statement of the ADS CFT correspondence. So the generating function of the CFT, which is just the expectation value of operator integrated to the source, is equal to the partition function of gravity in ADS, where certain object in the bulk, if I'm talking about the scalar, and certain scalar in the bulk, tends to the source as z goes to 0 as we approach the boundary. In particular, if we consider the stress tensor, then the source of that object is just a metric on the boundary of the ADS. So if we can compute this quantity in gravity, then by taking functional derivatives with respect to the source, we can compute all correlators in the CFT, and so we can solve this CFT. So in holographic CFTs, the leading connected Twopoint function, there is a disconnected term which stays at 1, but the connected contribution to a Twopoint function receives the contribution from the following Newton diagram, where we have two operators inserted on the boundary. There is a scalar propagating between them, that is dual with its operators. Then there is a graviton which exchanges between the two scalar lines. And the natural question is, what is the conformal block decomposition of this diagram? And you may think that since there is a graviton exchange, then this should correspond to the exchange of the stress tensor. So it should correspond to the conformal block due to stress tensors. And indeed, the stress tensor is there. The OP coefficient of the stress tensor is completely fixed by word identity and proportional to the conformal dimension of the operator O. And here, there is a square root in the denominator because it's just to normalize the stress tensor to 1 whenever I'm talking about the conformal block decomposition. And so the stress tensor contributes delta 1 of stress tensor. The stress tensor contributes the OP coefficient here times the OP coefficient here, which is delta 1 over square root of CT, delta 2 over square root of CT, which is this. It contributes, as I mentioned already, something which scales like 1 over CT, or 1 over n squared. So in addition to this contribution, however, this graviton exchange diagram contains conformal blocks of double trace operators. And the corresponding double trace operators are the operators made of O1 and the operators made of O2. And the OP coefficient of these guys are completely fixed in holographic theories. And as discussed, the OP coefficient of this guy scales like 1, the OP coefficient of this guy scales like 1 with CT, so it scales in the same way. It's 1 over n squared. But what's important is that the numbers are also completely fixed. So we completely know how this diagram is expanded in conformal blocks.
Sorry, what exactly do you know? Like the first number and the second number of both?
We know both. Yeah, here it's just fixed by word identity. Here it's fixed by reducing holographic computation. The correlator can compute, just explicitly computed, and you observe that it decomposes into conformal block of the stress tensor and conformal blocks of double trace operators, and you know the coefficients. And they scale like 1 squared.
So the first number is just from free theory, right?
Yeah. So
But the second
the second one is 1 squared.
Oh,
Yeah, the second one is 1 squared.
and how is it fixed?
Well, so this particular calculation, you just see, well, you know what the conformal blocks are because they're known functions. You know what the result is because you can compute the diagram of the graviton exchange. And then you just see, you just match the coefficients and observe that that's how it works. Now, you can ask a question, what happens if I start considering loop diagrams in ADS? And these are, of course, further suppressed by another factor of 1 over n squared, which is proportional to the ratio of the Newton constant to the size of the ADS to the power t minus 1. This is just a standard holography dictionary, which tells you that the central charge is equal to R to the power d minus 1 over G Newton. So in a way, we're going to discuss a situation where G Newton is very, very small in the units of cosmological constant, whatever ADS radius. Now, you can think of these loop diagrams in a different way. If you forget holography for a second, you can ask a question, what happens if we consider high energy scattering of two particles? So in this econal scattering, the amplitude is exponentiates, and it's fixed. The thing that sits in the exponential is the econal phase. And these loops contribute powers of the ratio of the Schwarzschild radius of the black hole, whose mass is equal to total energy, to the impact parameter. So when the impact parameter is large, then this contribution is small. So the iconal phase is completely given by a single graviton exchange. But as you increase the energy or equivalently decrease the input parameter, the black hole can, is going to get formed. And at some point, the iconal phase becomes complex, which corresponds to the creation of a black hole. And it would be very interesting to study this regime. However, this requires understanding loop diagrams in gravity, so it's complicated. Yet, you can simplify this question, and you can ask the question, what happens if I make one particle very, very heavy? So it has, so it corresponds to a black hole. And in this case, this problem becomes much easier. So the the scattering of a black hole and the light energetic particle can be described classically. And you can compute the scattering angle. It's a standard calculation. It's just a light propagating in the vicinity of black hole. You can compute the deflection angle, and from the deflection angle, you can exactly compute the iconal phase. And as I said, you can see what happens as the input parameter decreases. Your particle gets swallowed by a black hole, and delta becomes complex, which corresponds to absorption with black hole. You can compute the scattering cross section. It's going to be equal to the classical absorption cross section of black hole. So it's a kind of interesting regime from this point of view. Now let's go back to holography and see what it corresponds to. So, and of course, to go back to holography, you need to go back to the ADS space. Here is the black hole metric, which is asymptotical ADS, which we also call ADS Schwarzschild. And everything sits in this function f, and mu is just a number, which is proportional to the mass of the black hole. So what's interesting is that the coefficient of proportionality is G Newton over R d minus 2, where R is the size of the ADS. So if mu is 0, we just have usual anti-de Sitter metric in global coordinates. Now we can ask a question: what kind of conformal dimension would correspond to this black hole if we want to interpret it from the boundary point of view? And for that, we just need to use the standard ADS CFT dictionary, which relates conformal dimension to the mass in this way, and as I said, relates the central charge to the ratio of the radius in Newton. And so black holes with finite mu correspond to the situation where delta H over Ct is equal to mu, Thomson number. So if we want to describe black holes, we need to take this delta H to be very, very large. Remember that Ct, I'm interested in the regime where Ct is extremely large, it goes to infinity. So if I want to describe black holes, I need to take delta H, or conformal dimension of the heavy operator, to also be very, very large. So I scale both of them to infinity in the same way with a ratio that's fixed. And now we can ask a question, what happens? So from the point of view of the amplitudes, these kind of diagrams survive. This kind of diagrams are suppressed. Basically, you enhance the diagram because the mass of this guy is very, very heavy. And from the point of view of the dual, and as I said, the physics becomes classical. From the point of view of a dual CFT, the contribution of the stress tensor is as before, delta heavy over square root of Ct, delta light over square root of Ct. So the difference with what was happening before is that delta heavy also scales with Ct. Before, if we consider two light operators, this would be number of order 1, we would get 1 over Ct, which is 1 over n squared. However, now we consider heavy operator, so this is the same as delta heavy over Ct, which is the same as mu. That is to say, in the CFT language, the contribution of the stress tensor to the scattering of one heavy and one light particle scales like mu. Now, the double stress tensor contribution, you can show that This guy scales like delta heavy squared over CT. This guy scales like delta light squared over CT. So that scales like mu squared. So the so in the regime where mu is finite, all double stress tensors, single stress tensors, and multi stress tensors contribute powers of mu. And this power k depends on how many t's you exchange. Okay. So we will be interested in the contribution of all operators of this type. So you can have one stress tensor, you can have an operator which you make out of two stress tensors, k stress tensors, and so on. And we call the result of all these contributions the stress tensor sector of correlators. So these operators we call multi-stress tensors, and all these contributions are stress tensor sector. So in particular, in D equals 2, the stress tensor sector is nothing but a Virasoro vacuum block. So in D equals 2, in two-dimensional CFT, there is Virasoro symmetry, and because of that, this block can actually be computed. And that's some interesting function. In high dimensions, the situation is much more untrivial. And you can ask me, why do you care about this stress tensor sector if you just mentioned that there are some other operators, like double trace operators? And the answer is basically there are ways to decouple these double trace operators in holographic theories by at least a couple of ways. There are more. So one way to decouple them is, for example, we can take conformal dimension of a light operator to be large. And also some observables like the iconal phase that I mentioned that turn out to be insensitive to double traces. In other words, there are all sorts of physics questions that you can ask which are insensitive to double traces, which only care about the stress tensor sector. So, that's going to be our goal. Our goal is going to be discussing the contribution of the stress tensor, of the multiples of stress tensor to the Twopoint function of two heavy and two light operators, and then interpreting the resulting physics in various ways. Maybe now is a good time to pause for questions. It's basically two graviton exchange. So when you have two light particles scattering, two graviton exchange is heavily suppressed when you have a very small G Newton. But here, because one particle is very heavy, it's enhanced. So it's fine. The one graviton exchange scales with mu, which is basically the mass of the black hole in some units. Two graviton exchange scales with mu squared, and so on. More questions? I don't know if anybody wants to ask a question online.
I see you here.
Okay. So, in the rest of my talk, I will first talk about leading twist multi-stress tensors. And I'll define a limit where these guys contribute, and I'll show how this object can be computed. And then I'll talk about applications. How much? When did I start?
20.
So I have what, like another 40 minutes, something.
Yeah.
Okay. And then the applications include generalized Catalan numbers. Turns out that Catalan numbers play a prominent role in this whole story. Then there is a holographic calculation, which completely agrees with. So this is going to be a CFT calculation because it's bootstrap. There's a holographic calculation that completely agrees with the CFT one. And finally, I'll talk about some physics related to going beyond the limit. All right. So
kind of calculate the complex space. Right?
Yeah.
And then probably you'll tell us the probability of particles.
Oh, thank you for asking. I'll mention, unfortunately, yeah, this is one of the very interesting things that you can do with this. But unfortunately, I won't be able to spend much time on this. So I'll just mention, and then if you want, we can discuss it in more detail. So we're going to compute the two-point function of light operators in a state which is created by heavy operator time minus infinity and time plus infinity. And this can be viewed as a two-point function of two light operators in a heavy state. It can also be viewed as a four-point function, heavy light four-point function, where the cross ratios are related to the positions of the light operator. So the only thing that matters, first of all, there's some minus infinity here, it's heavy, there's some heavy guy here, and the only thing that matters is the relative translation in time between the light operators and the relative angle between the light operators in the sphere. So here we are on the sphere, here we are on the sphere of radius r. And the cross ratios are related to these objects in this simple way. In particular, you can see that as you take these two operators close together, so delta t and delta phi go to 0, both z and z bar go to 1, and that's basically the regime where the two light operators get close to each other. Because remember, actually, there should be 1. I'm sorry. Okay, it's a type. It should be 1 here. So this is the regime where both z and z bar go to 1. Oh no, this is okay. So, no, sorry, this formula is okay. The formula, you know, when I was showing you the conformal block decomposition, the two light operators appeared at 1 and z and z bar. So taking two light operators together corresponds to taking z and z bar to 1, which corresponds to taking delta t and delta phi to 0. So the stress tensor exchange, is completely fixed because, as we discussed, the OP coefficients are completely fixed by the word identity. The twist of the stress tensor, which is defined to be the spin minus the conformal dimension, is equal to d minus 2, which is the minimal twist for any conserved current in the dimensional CFT. So there's nothing particularly exciting. Everything is fixed. However, things become much more interesting when we go to order mu squared, which, as you remember, is coming from the double trace operators, where we have double stress operators, sorry, where we have two stress tensors, and then we can insert a bunch of derivatives in a bunch of boxes. So the reason why it's going to be much more interesting is because there are infinitely many of them. In particular, I will classify them by the twist. The leading twist double stress operators are the ones where I just insert derivatives. I don't contract any indices, and then I symmetrize everything. The subleading twist is when I start contracting the indices or I insert the boxes. So subleading means the twist is increased by 2. And then I can continue doing this. So there's an infinite number of towers for each twist. Note that for any twist, there are infinitely many operators. So these leading twist operators are labeled by this pin. Then for subleading twists, there are infinitely many operators, which are also labeled by this pin. So then I can start considering triple stress tensors and so on. And I can consider k-stress tensors with leading twists. And for them, the twist is k times t minus 2.
So like on the bulk side, is it one block diagram? Right? It's two gravities.
That's right. All of these guys correspond to basically one block diagrams. Yes, all of the double stress tensors. And then triple stress tensors would be two block diagrams and so on.
And probably like this specific one, like the bubble.
Yeah, some specific diagrams. Yeah. But these are the only these are the only diagrams that survive in this limit when we take the mass of one particle head. So, so what's the physics? So I mentioned that I'm going to be interested in the lowest twist operators. Why should I care? And the reason is that as you take the OPE and make X close to being null, you approach the light cone, the OPE is dominated by the lowest twist. I can easily see if you allow operators with spin L here, then this indices must be contracted to something. The only something here is X. There's a bunch of X's in the numerator. And to maintain scaling, what you're going to have in the denominator is X to the power twist. So now, if I consider the situation where X is null, so all the components of the vector X are finite, but X squared goes to 0, you can see that it's the operator with the smallest twist that contributes. And that is reflected in the near lightcone behavior of conformal blocks. So conformal block of operator Tk scales like 1 minus z bar to the power k times d minus 2 over 2 for leading twist operator. Basically, you have twist over 2 sitting here. Interestingly, it was noticed that the OPE coefficients of the leading twist operators are not affected by higher order gravitational terms in the bulk. So you can try to do holography with extra high derivative terms in the bulk, and you can try to compute some of these OPE coefficients. And what you observe is that these OPE coefficients are not affected. So we can keep all, remember that each t to the k comes with the power of mu to the k, but now I'm telling you that each leading twist t to the k comes with the power of 1 minus z bar to the power k d minus 2 over 2. So that means that we can keep all of them, all the leading twist t to the k operators, by keeping this quantity, which is mu times 1 minus z bar d minus 2 over 2 fixed. That's going to be the limit that we're going to take. So this allows us to keep the contribution of all leading twist operator for any k stress tensor tower. And then it turns out that this quantity, so this is the quantity which is most analogous to the spherosaur vacuum block, and it has some physics in it. But for now, let's just, and as I mentioned, this is a quantity which is universal in holography. So different holographic theories will not change the result. So no matter what holographic theory you try, it's going to be always the same. So this is a universal sector. That's why we're interested in it partly. So it turns out that we can actually find the whole thing, we can solve the problem without doing any holography. So the way it works is by, well, first of all, before you solve anything, let me point out that order mu squared, or rather mu tilde result is just the contribution of the stress tensor. It's the single stress tensor in the light cone limit, in the near light cone limit. So this contribution is just this factor, which is just a scaling factor, times this interesting function f3, which is 1 minus d to the third power times hypergeometric function, where a is equal to 3. So any fa.
Can I ask? Yes, if you can hear me. Could you please repeat the statement about high derivative corrections not contributing somewhere, and how is it proved?
Yeah, so the question is about the statement about the high derivative correction. So, so in this paper, some two-point functions. Well, in this paper, some OPE coefficients of scalars and multi-stress tensors were computed, and it was pointed out that for leading leading twist multi-stress tensors, these are the ones that I'm discussing here. These OPE coefficients do not depend on the addition of high derivative terms in the bulk gravitational Lagrangian. So in principle, you can try to play with the holographic models and add high derivative terms in the bulk. That in principle changes your 3-point function of stress tensor in the boundary CFT. So it changes your holographic data. However, this particular P coefficient of leading twist multi-stress tensors are not affected. So there's some degree of universality. Did I answer your question?
Yes, okay, thank you.
All right, so this is other Matilda result. Now, again, it's just a stress tensor, so it's kind of not so exciting. But what is things become much more exciting when you assume the following answer. And I'm not going to explain to you, how this ansatz came about, but no, we just observe that it works. In particular, so what's the nature of the ansatz? So at order Matilda squared, we postulate that the only terms that appear in the answer are f3 squared, f2, f4, and f1, f5. So first of all, in each term, there with some coefficients in front of them. So in each term, there are two f's, and the sum of all subscripts in f sums to 6. Now, at order mu cube, we claim that the allowed terms are the terms which contain 3 f's, and the sum of the subscripts sums to 9. Of the subscripts in these terms are 9. 2 plus 3 plus 4 is 9, right? And so on. And similarly for all higher values. So we claim that this form completely describes correlator. Now, as soon as you fix this ansatz, you can actually bootstrap the model and serve for all these coefficients order by order. And the way it works is, let's consider a stress tensor term. So the stress tensor, as I mentioned already, is a simple function which is proportional to f3. But if you expand this f3, if you write down what this f3 is, it's some explicit function which just contains a log. There is some log times some polynomial of z, and then actually it's not a polynomial, it's a series of z, and then there is something which doesn't have a log, and all these coefficients are known. Now we can interpret it in the cross channel where we fuse the heavy and the light operators together. And in the cross channel, it must be that, so in order to reproduce this result, it must be that the anomalous dimensions of the heavy light operators have this form, where L is the spin of, so in the cross channel, we have double trace operator. The only thing that propagates a double trace operator is heavy or light, and they have spin L, and we have end boxes inserted. So it must be that the anomalous dimensions of these guys behave like this, with gamma's unknown coefficients at this stage. Get back. Okay. Okay, great. So the anomalous dimensions have this form, and the P coefficients also have this form. So by matching this to this, we determine completely the anomalous dimensions and the P coefficient. And then we notice that the logs, so if you go to order mu squared, the log squared terms come from anomalous dimensions. So all the log squared terms from the anomalous dimensions that we just determined. So all the log squared, because this is basically mu times something, so mu squared times log squared comes from second order expansion of z to the power gamma. So all the log squared terms are completely determined. And since the ansatz is so rigid, that determines all coefficients in the answer. In particular, the complete answer at order Matilda squared is this. So now you recognize this power, just scaling. Now we recognize these guys, which is part of the ansatz. And then these are the coefficients, which, as you see, are completely determined in terms of the power of the light scale. And then you continue this. You continue to cubic order, to quartic, and so on. This way, you found the whole function. In particular, from here, you may say, okay, you know, it involves some heavy operators, but the reality is that from here you can extract the OP coefficient of any operator with the multi-stress tensor, because what enters so the form of the OP coefficient of any operator with the multi-stress tensor is this, and the form, you know, when you take the heavy limit, only the leading term survives. So from this product, you can actually deduce the OP coefficient of light operators with the multi-stress tensors. In particular, the OP coefficient of light operators with a double stress tensor is given by this formula, where AL is, you know, something which I didn't have space to write, but it's a known function of L. L is the spin, and BL and CL are these functions. To summarize, we can compute all these OP coefficients. And we can compute them to any order in the tilde. So one thing to remember is that everything we compute is only done to leading order in 1 over CT. And we never used any holography, but we do recover in the holography, some of the OP coefficients were computed, and what we got, of course, agrees with them, and of course we have actually the whole thing. And what's interesting is that this correlator exponentiates in the sense that it has this form where this curly f has a finite limit as delta light goes to infinity, very large. And that's going to be useful later. And another interesting thing is that we can simplify the result further by taking the large volume limit. So far, we've been discussing the situation where CFT was in a sphere of radius r, but you can take the limit when the radius of the sphere is large, then the large volume limit, all the operators with derivative die, and the result is an expansion in powers of mu times delta x minus and delta x plus cube. There is some radius. Well, anyway, so there is some function that you get, and we can compute, all terms in this function. So it's a 4-dimensional result which comes from Bootstrap, and it's the we can compare it later with the result from holography. Okay, so now we know the correlator.
So you're computing some things and you get it seems universal answers which do not depend on the theory.
Right.
So why is that, and what does it correspond to on the both side?
No, it's a good question. So let me just say that this corresponds to holographic theories in the bulk, where you can add all sorts of high derivative terms. Now, it's definitely not the case that these OP coefficients that I was talking about would be true in any large N CFT. So that's definitely not the case. But if you consider theory where there is a large gap for high spin operators in the bulk, if you consider CFT with a large N CFT with a large gap for spinning operators, then that's going to be a universal answer.
Do you have anything similar in flat space? Is it something like soft theorems, or what is it?
That's a good question. I don't know. That would be, Now, generalizing some of this to flat space definitely be an interesting direction. We haven't done any of this. So okay, now let's discuss some application. So first, let's talk about the Catalan numbers. So how do the Catalan numbers show up? I missed the reference. So there's a very nice paper by Fitzpatrick, Kaplan, Walters, and Juan. I apologize. I definitely thought I included this reference here, where they pointed out that in two dimensions, well, first of all, in 2 dimensions, the Virasoro vacuum clock is known, the analog of what I was just discussing. And they showed that in the limit as it goes to 0, this curly f, which appears in the exponential, is proportional to a log, first of all, and the coefficient of proportionality is given by this function, which is the solution of the simple quadratic equation, and in addition, is the generating function of the Catalan number. That is to say, if I expand this B2 in powers of mu, then the coefficients that appear here are the Catalan numbers. So these are the Catalan numbers. And one way to think of them, there are a few ways to think of them. One way to think of them is to consider a partially ordered set where this arrow means that this object is greater than this, and this number is greater than this number, but it doesn't tell you anything about the ordering of this number and this number, for example, and then so on. This, of course, is the same as the number of 2 times n Young tableaus. That's basically the same. So you have some numbers which are increasing this way and this way. So how many of such tableaus are there for n equal 3? So for n equals 3, as so for n equals 3, as we can immediately see, there are 5 such tableaus, because I can make, well, basically these are the corresponding tableaus that satisfy this property, that the numbers increase as you go to the right, and they always increase as you go up. But no, nothing you can say about this number and this number, for example. Okay, and another way to think of Young tableaus is it's a number of binary trees with n+1 leaves. So how many binary trees are with 4 leaves? It's 5. So these are the corresponding binary trees. And there are other ways to think of Young tableaus. There are many ways to think of them. So there are many ways you can think of them. And it's interesting that they appear here in this in the Virasoro vacuum loop. Yeah, so that was explained in this very nice paper called Hawking from Catalan. So this gets here. Okay, I didn't mention. So the equation for the generating function that I just showed you can be generalized to a nonlinear differential equation, which the block, or rather logarithm of the block, turns to satisfy. Remember, the original equation was b equals b squared plus mu. So now, if you simply add a bunch of derivatives, it turns out that the logarithm of the block satisfies this equation. And, well, as I mentioned, the solution is known, and it satisfies our answers, suitably modified for 2 dimensions. So there's F2, there are F2s here, and so on. So that's a known story. But you can ask a question, what happens for higher spin algebra? So consider heavy light block of the W3 algebra, which you remember is the algebra where, in addition to the Virasoro, you also have a spin-free current. And let's now consider, by saying that the block is heavy, what I really mean is I take the spin-free charge of my primary to be very, very large, and it scales with the central charge. So I take this ratio finally. It turns out that the result satisfies the same answer. The result is known again. It's slightly more non-trivial to compute it. Well, actually, there are some subtleties there, but let's say the result is known. It satisfies the same answer. And moreover, you can take a limit z goes to 0 and again observe that the coefficient in front of the log is some function which, for certain values of the charges, satisfies the generalization of the Catalan equation. So this is a generalization of the Catalan equation, which a corresponding object in the W3 case satisfies. So all this is in 2 dimensions. Now it turns out that you can make it into a differential equation, and the full logarithm of the conformal block of the W3 algebra satisfies this differential equation. So this is a generalization of the Virasoro story in 2D, and similar patterns happen for high WN algebra. So that's what happens in 2D for high spin algebras. But it turns out that the structure of the near lightcone 4-dimensional result is very similar. So first of all, again, as you take z goes to 0 limit, the log n terms disappear. In principle, there are log n terms, but they all disappear in for this particular case. And there is some function which sits in front of the log, and the numbers that appear in this function are the numbers of linear extensions of some partially ordered set. So this partially ordered set is slightly different from the Catalan. Remember that the partially ordered set that define the Catalan numbers is this, and now I just add a bunch of dots in the middle. So it's going to be my new partially ordered set. So the story for the near lightcone correlators in D equals 4 is very, very similar to the story of 2-dimensional conformal field theory. The only difference is the partially ordered set is slightly different. And again, the story repeats for any number of dimensions. Unfortunately, we don't yet know an equation for the generating function for these guys. If you knew them, then you could possibly write down a differential equation and solve. So that's the Catalan number story. Are there any questions?
So do you work only in even dimensions, right? Is it because like you have simpler formulas for conformal blocks?
Yeah, that's basically because of this. And it's very, again, another thing that would be nice to do is to generalize it to dimensions, which we haven't done. But it's clearly going to be, no, it's not going to fall in the same category because here 4 dimensions correspond to W3, 6 dimensions correspond to W4, and so on. So it's not so clear what the odd number of dimensions correspond. No questions. So I have like 10 minutes. I probably should speed up a little bit. So as I mentioned, there is a holographic calculation which reproduces the bootstrap calculation in the regime where delta light is much, much larger than 1, but still much smaller in central charge. And I'm just going to sketch it. I'm not going to go into details. Basically, the point is that in holography, this correlator in this regime, this is in the classical regime, where in holography, the logarithm, this curly f is simply the regularized length of the geodesic, which connects the points of insertions of light operators on the boundary of radius Schwarz. And as soon as you realize that, then you just need to compute the geodesic length. What's interesting here is that the relevant, because you're interested in the leading twist calculation, the relevant object is not going to be a 5-dimensional radius Schwarzschild. Instead, you do some scaling, and the relevant metric is a 3-dimensional metric of this type. So one can ask a question, well, no, it's an interesting question, what's the significance of this metric? But once you have this metric, you can just do the usual calculation of the geodesic. There are two Killing vectors. You just compute, do the usual tone and dance, and compute the length, and there is some answer. So particularly in 2D, you recover the Virasoro block, of course, if you should. Yeah, unfortunately not. Yeah, that's a good question. I don't know. It doesn't satisfy equations of motion. It's not a solution of Einstein's equations. Yeah, but there is no mu. But there is no mu in metric. Mu is gone. Well, it's not a it's not a shock wave. It's not a shock wave at all. So yeah, it's different physics. That's for sure. We sort of understand like the kind of physics that shockwave describes in ADS in particular. But this guy describes different physics. Yes, that's right. Anyway, so we do this calculation. There's some answer. Actually, there's a full answer. This is how the result looks like. It's related to some. Unfortunately, it's not like super nice. It's not as beautiful as it is in 2 dimensions. But you can write in terms of elliptic integrals, and you can expand it. And this expansion, again, is in the power of mu delta x minus delta x plus cube. And it's exactly the same formula as the one that you get from Bootstrap. So just a very nice consistency check. Okay, so that was the holographic calculation. And the third application of the story that I wanted to discuss is the situation when you go beyond the limit twist. So what happens as you go beyond the limit twist? First of all, you can actually do Bootstrap beyond the limit twist as well. And you can observe that the results agree with some. You have to suitably modify the ansatz, and there will be new data that you will need to fit in because it's no longer universal. But in principle, you can do it. It's just becoming non-universal, complicated. And then you can ask a question: what happens in non-holographic theories? So in particular, there are finite gap corrections to this OP coefficient. If you have finite gap, there are corrections, and you can ask the question: is there any universality that remains in the large for all large N theories? And one answer to this question is to some degree yes. And to see it, one can consider large N CFTs at finite temperature. So in finite temperature CFT, well, first of all, in large N CFTs, one can show that the stress tensor thermalizes. That is to say, the 1-point function of the stress tensor in a heavy state is equal to the thermal value of the 1-point function of the stress tensor, where the temperature is determined by the usual relation between the energy and the free energy. And that's basically a consequence of the large N, which is the thermodynamic limit, plus the fact that this is fixed by the word density. Now, consider this object, consider the 1-point function of a K stress tensor at finite temperature. So because of the large N factorization, this is just the 1-point function of one stress tensor to the power K. And because this is fixed, this is just delta heavy, so this is just delta heavy to the power K. So this is completely fixed in all large N CFTs. So the statement that the K stress tensor thermalizes is equivalent to the statement that this object is equal to the same object at finite temperature, but this is a fixed, this number is universal. It's true for any CFT. So if the stress tensor thermalizes, then this statement must be true. And this is the statement about leading delta behavior of multi-stress tensor OPE coefficient in any CFT. So in any CFT, the leading delta behavior of the OPE coefficients must be the same. And it's actually, it turns out to be the case. So you can compute the OPE coefficient. So some of the OPE coefficients in holographic theories we observed already. You can compute the OPE coefficients in free theories. And indeed, you observe that there is universality. The coefficient, the leading behavior of the OPE coefficient in all Argentine CFTs is the same. And that is equivalent to saying that the T to the K stress tensor operator thermalized, which is not true about other operators in large systems. So let me summarize. So we have a procedure to compute heavy light correlators to all other mu using bootstrap and ansatz. The logarithm of the correlator in d-dimensional CFT is the same, the form of it. It has the same form as the corresponding object for W d over 2 plus 1 algebras in d equals 2, amazingly enough. And for Wn algebras, we can write an equation which this object satisfies, for d equals 4, not yet. We check that holographic computation agrees with bootstrap, and we observe some degree of universality related to thermalization. Now, some of the questions that would be nice to answer. But first of all, it would be really nice to find closed form of the heavy light correlator in the d equals 4. Maybe it's related to finding generating function for that for these numbers that I mentioned. A related question is whether there is some high symmetry algebra that sits behind these lightcone correlators. If it's very similar to W3, maybe there is some kind of algebra which is relevant. Maybe there's some symmetry, some hidden symmetry in CFTs, which governs the near lightcone behavior of correlators. Then I believe that this whole technology is going to be useful in understanding thermal large CFTs. So holography, of course, is quite useful, but for certain questions, this technology, the CFT technology, might be more useful. And then you asked a question about this high energy scattering and gravity, which this whole story is relevant to. Unfortunately, I didn't have much time to talk about it, but basically, well, yeah, let's talk about it after I'm done. But yeah, it's an interesting question, and this whole story can say a few interesting things about it, which unfortunately I don't have time to describe in detail. So thank you very much.
Questions? Here or in Zoom? And we did it by diagonals. It's some conceptual explanation to diagonals.
Yeah. So yeah, it's basically what happens when you take the mass of particle to the large. It propagates on a geodesic. It's a geodesic approximation. Yeah, it's you can solve it. Otherwise, no. Well, okay, so let me talk a little bit about this, this story. So here it's a particular limit to this, where no, you don't need to do, like what they do obviously is much more generic, but in particular you can take a limit of their calculations where the incoming particle is a probe, the sitting particle is a black hole, and then of course, as I mentioned, everything becomes classical. It's a classical question of light propagating black hole. And then you can compute this delta to all orders. And you can observe that finite. So it's a ratio of the Schwarzschild radius to the input parameter. And you can, let's say, decrease the input parameter. So you increase this, this ratio. So it's and at some point, a cut develops. And there is some analytic structure, cut develops, and this function acquires the imaginary part. This imaginary part is large. So the point where this cut develops is precisely the point where your particle falls into a black hole. This is the last circular, well, this is the circular orbit of light, basically. And so, okay, so everything is consistent. You observe the large imaginary part, absorption by a black hole. And there's an interesting effective description of this in terms of, so the delta, interestingly enough, is related to the anomalous dimensions of the operators in the cross channel, heavy light operators in the cross channel. So what happens here is there's some effective description where the anomalous dimension of these operators becomes complex. People, that's an interesting thing in CFTs. What happens when there's obviously some non-linearity that happens on the anomalous operator. Yeah. Yeah. So you can compute all. So there is some expansion. So this is your iconal phase. You in this regime where there is a probe and a black hole, you can compute all terms in this expansion. Yeah. Yes. You sum it. It's some no function, and at some point, there is some radius of convergence, and at some point there is some cut. So that's exactly the point where this black hole stops absorbing it. And that's exactly, and this imaginary part is large. So if you compute the cross section using the standard formulas, you get the right geometric cross section. So nothing surprising here. But what I was trying to say is that there is some interest, a little bit of physics behind it. So you cannot do the same exercise for light particles, obviously. Yeah, you have to do a little bit of work to get to that result that I mentioned to you. You have to, first of all, you can take the flat space limit of this whole, but ADS. Then you can keep mu finite, and the only thing that changes is the input parameter. So you keep mu finite, the black hole mass is fixed, and what changes is the input parameter. This is the position of these guys, and you can then you can see what happens as this input parameter goes beyond critical value. And what happens is what I just told you. Now, and you can also take a flat space limit where things are obviously easier, but okay, you don't have to. Now, also wanted to make a comment that the physics of this, the CFD physics of this is the complex anomalous dimension of this heavy light double trace operators. So if you approximate this story to the light scattering, you may think that there will be complex anomalous dimensions for light operators, double trace operators, and that will describe the creation of a black hole in the light scattering process. But you know, that's just. Well, that's a very good question. That's a good question. I think that depends on what kind of complex anomalous dimensions you have. But one interesting example where you have complex, well, look, we are going tangentially to this whole story, but one interesting example that appears in the CFT with complex anomalous dimensions is when the mass of the scalar goes beyond the Brettel-Lochner-Friedman bound. So when you go beyond the BF, at the BF bound, as you know, huh? It's negative. The mass squared becomes negative in the units of ADS radius. But what happens is, you have two solutions to, well, generalized equation, which is like delta times 4 minus delta equals mr, and there are two solutions to it. But as the mass goes to BF bound, these two solutions get closer and closer. So at some point they become equal to 2, talking about 4-dimensional CFT. And these two solutions, they just correspond to two CFTs in the boundary, which are related by flow by double trace operator. So that's understood. Now, what happens as you go beyond it, there is some complex dimension opens up. So this operator requires complex dimension. You can ask a question, what happens there? And different people can tell you different things, but I like to think of it in terms of flow, that your conformal theory is no longer conformal, but instead it flows. It develops, it flows to some new theory in infrared. So in particular, if it's a little bit below the BF bound, it's this flow with the beta function, which is almost constant. But that's a totally separate statistics. No, this is much higher. We're talking about operators which have very high conformal dimension. BF bound. No, it's not related. No, entirety bound for scalars is delta equals 1. 1 in 4-dimensional CFT. In any 4-dimensional CFT, entirety bound for scalars is delta equals 1. But here, what happens is these two scalars, both conformal dimensions go to 2, and then they become complex. So the two CFTs get very close together, and then they sort of go off.
Other questions?
Yes. Well, I mean, that's right. That's exactly what happened. Well, that's how you explain this flow in the CFT. So indeed, you have a tachyon on ADS, it condenses, and the equation, the nonlinearity in your equation of motion becomes important. So that nonlinearity presumably does something once the profile for your tachyon becomes large in the infrared, and then deep inside the ADS. So you have to think of some ways to, you know. That's right. But the question is, what's the infrared theory, and that depends on the dynamics in the deep in the bulk language.
Okay, I guess we don't have any other questions, so let's thank speaker again.